Hello, can you hear me? Okay, good. Okay, we are starting. Okay. Everything is good. Okay. So, hello everyone. Welcome to the last presentation of this semester. So today we will focus or discuss about another interesting direction, which is related to privacy enhancing technologies. And in this session, we have Valentine. Valentine is a first year bachelor student studying in, last year bachelor student uh, studying in computer science department at ETH. He's interested in working in the direction of privacy and information security, and also on the system level implementation of these techniques. And today he will be presenting one of the latest works. And I think with that, yeah, Valentine, go ahead.
Yeah, hello and welcome to my presentation of Orion, a fully homomorphic encryption framework for deep learning. It was presented at ASPLOS in 2025 in Rotterdam, Netherlands. And first, I will give you a short overview of what fully homomorphic encryption is. And yeah, then I will continue with my talk. So what is fully homomorphic encryption? Basically, the promise is that we can compute unencrypted data without having to decrypt it. So we send the data to the cloud, they compute on the data, and then they send us back the results in an encrypted format, and we can then decrypt the final result. So the cloud or the server never sees our data or intermediate results. Why it matters? I mean, it's a privacy concern. So especially in a ecosystem where there's more and more machine learning applications, especially for healthcare or finance, where sensitive data is involved, it is important that we keep this data private and the ML provider doesn't see our healthcare or finance data. But the problem is that FHE currently is very computationally expensive. So there are different FHE schemes. We have different approximate schemes, exact schemes, and Boolean schemes. But because Orion is focused on neural networks and we don't need much exactness there, they use an approximate scheme. They use especially CKKS. In this FHE scheme, you have a clear text message, M, which is a vector, and then you pack this message into a polynomial using this packing method. I mean, this is the naive way to do it. You basically just, this is a normal polynomial of high degree, and you put every data element as one of the coefficients of this polynomial. Then we take this polynomial, the plaintext polynomial, and encrypt it in the following format. There's a public parameter that's getting sent with the ciphertext to the server or the cloud. And there's a secret key, which only we know as the sender. And then we add this to M, the plaintext polynomial, scaled by a factor lambda. And then we also add an error. We add this error because without this error, it would be much easier to guess the secret key or the message, parts of the message, if you were an attacker. So we need this error to be more secure. This scheme supports the following SIMD operations. Those are SIMD operations because, I mean, we are working on polynomials. So we can work on each of the coefficients separately. So that's why we use SIMD. We have element-wise addition, element-wise multiplication, and cyclic rotation. CKS is an approximate scheme, as I said before, because this is a deep learning application. We can use this, and the small errors are not that important in this application. But as said before, there are some constraints. Because we add this error polynomial, And for example, if we do a multiplication, this error gets larger and larger with each multiplication. So if at some point we want to decrypt again, the decryption fails. So basically, after a certain number of multiplications, we need to remove the excess noise. And we have a multiplication budget. So we have a budget of how many multiplications we can compute until the multiplicative budget, also known as levels, is basically used up. This operation, when we remove the excess noise and retain some of the multiplicative budget, is called bootstrapping. And this operation is very computationally expensive. So now I will go into the machine learning or deep learning part of it. Basically, I mean, I think you know that, but a typical layer consists of linear or a convolution layer. And this step involves a matrix vector product. And then from the output, we need to apply an activation function. This is ReLU or sigmoid or other activation functions exist. In the linear convolution layer, because CKKS only works on vectors, we need to vectorize the matrix in this product somehow, such that we don't have matrix vector products, but only vector-vector products. In here, we use the diagonalization method. We basically take the diagonals of this matrix and rotate the vector multiple times to get the output as if we would have just computed the matrix vector product. This process uses two operations, pmult and hrot. Pmult is basically a multiplication between, when we go back, between a plain text and a ciphertext. One is unencrypted and one is encrypted. This is because the matrix, we don't have to encrypt that. So those colorful vectors are not encrypted, and the gray ones are encrypted. So that's why we use pmult. And hrot is just rotating the gray vector, so the encrypted vector. This whole process consumes one level. So if before we could, in theory, do, I don't know, like maybe 20 multiplications. After this step, we can only do 19 multiplications. So it's like we use one level or one multiplicative budget. Then after this step, we have to apply the activation function. The thing is, we are working on the level of polynomials here. So we have to use a polynomial, but most activation functions are not inherently polynomials. So we approximate this activation function with a very high degree Chebyshev polynomial and apply it. The problem is that this step consumes a lot of levels, so it increases the noise a lot. For example, ReLU consumes 14 levels. So yeah, that was the background. Now let's go to the executive summary. Using neural networks with FHE faces three major barriers. We have inefficient data packing strategies, performance degradation due to manual bootstrap placement, and lack of programmability. The goal here is to build an automated, efficient interface for FHE based on deep neural networks. And they use the key idea here is that we use a single-shot multiplex data packing. We optimize the neural network compute graph to place the bootstraps, and we provide a PyTorch integrated framework to improve programmability. Orion provides an automated framework for FHE deep learning that improves performance and programmability by using single-shot multiplexing, halving strided convolution depth by 2, and automatically placing bootstraps to minimize latency, and also providing PyTorch, a PyTorch integrated API to improve programmability. The key results are that Orion improves performance by 2.38 over state-of-the-art on ResNet 20. It was the first to run ResNet 50 on ImageNet. This took 8.98 hours. And also the first to do high-resolution object detection using YOLO v1. Yeah. So for the talk outline, I will first go over the problems Orion is trying to solve and give you an overview of how they're solving them. Then I'm going into each of the key features and explaining them more in depth. Then I will go over the evaluation results, strengths and weaknesses, and then we can have a discussion. Okay. So the first problem, data packing. That was the first step when we take a vector and create a polynomial out of it. The thing is, some operations like convolutions require a specific data layout. So if we just do it naively, we waste a lot of computation. Yeah. Then with the bootstrap placement. The thing is that if you look here, we have the cost of certain operations. Those operations we've used before in the matrix vector product. And you see the latency is really low. But here in the bootstrap, the latency is very high, and also with the number of levels, it grows super linearly. So the thing is, it's really important where we place those bootstraps such that we have low latency. Exactly, poor placement equals excessive latency. Then on the programmability, with prior tools, you need a lot of FHE expertise to basically implement those neural networks. And also you had to manually place bootstraps where you wanted them, and didn't have like automatic bootstrap placement, or not as good as Orion. Orion solves this by first introducing single-shot multiplex packing. It's a special kind of novel data layout for convolutions, which supports arbitrary stride and other convolution patterns. And it reduces like the consumption of multiplicative budget from 2 to 1. They also have automatic bootstrap placement, in which they construct a compute graph and solve the shortest path. And this reduces number of bootstraps and also latency. Then they provide a PyTorch integrated framework, which builds on top of the PyTorch neural network model. And it makes it really easy to load pre-trained models and convert them to FHE models directly. So let me now, in the next part, we're going into each of the key features and explaining them more in depth. First, the single-shot multiplex packing. What they did is that they first represent the convolution up here as a Toeplitz matrix. You see here, basically, the first row represents as if we would have placed a filter on the top left. So we have A times 5, 6 times B, 8 times D, and 9 times E. So it would have been as if we would have placed this part up here. Then they can implement a bunch of optimizations on this matrix. This is the baby step, giant step optimization. This is similar to the diagonalization method. It's actually improvement on it, where they reduce the number of rotations. In this example, from before we had 6 rotations, and here we have 5. It's the same method, but just a little different. And then they also, did you see this down here? If you look at this matrix, you have a lot. You don't have a lot of diagonals where there are only zeros. So they basically transform this by switching rows to create a matrix which is equivalent, but they have a lot of zero diagonals here. So basically, if you apply the diagonalization method to this matrix, you can cancel out a lot of computation. So this reduces the number of rotations drastically. They also reduce the strided convolutions from 2 levels to 1 level. They do this by prior works. They used 1 level to do a normal convolution, and then they masked and collected the correct elements from the result. And Orion does this in 1 step, and they basically pre-compute this mask and collect step into the weight matrix. It also, this approach supports arbitrary convolution parameters, and it has fewer rotations. You see 1.65 to 6.41x reduction. Okay, the second contribution is automatic bootstrap placement. Basically, if we have as an input a neural net, this is a simplified version without activation functions. It's just linear layer or convolutions, whatever. You create a directed acyclic graph, where the nodes are basically, okay, so on this row, there are all the nodes which correspond to this layer in the neural net. And on the columns, we have the levels. So each node corresponds to a layer level pair. And then to go from one layer to the next, we have different operations. Each operation is weighed by its latency. And the red edges are here bootstrap operations. So you weigh all the edges with their latency, also the bootstrap operations, and then you find the shortest path from input to output. When you did this, you can basically look at where the red edges are in your shortest path. And with this, you have the optimal placement. So the path where you have the least latency. This algorithm also has linear complexity network depth. And yeah, I said it already, it has optimal placement. Okay. Then here's a code example for using their Orion framework. If you know PyTorch, it looks pretty similar. So you can create a convolution layer, you can create a batch norm, you can create ReLU, and basically use it just as you would with PyTorch. And it handles all the stuff like bootstrap placement and other complicated FHE stuff in the background. And it's not like exposed to the programmer. So that's, yeah, handy. Okay, so let's go to the evaluation result. They used different benchmarks, and they used MNIST with 3 networks, C410 with also 3 networks, Tiny ImageNet with MobileNet and ResNet 18, and Pascal VOC with YOLO V1. This is for object detection. The hardware they used was an Intel Xeon Platinum running on 2.3 gigahertz with 512 gigabytes DRAM. This is a lot of DRAM actually. Yeah, and the key metrics they used was latency versus prior works, rotation count reduction, bootstrap count, and accuracy preservation, all versus prior works. And they validated this by comparing the outputs of their framework with normal PyTorch unencrypted outputs. Okay, so the key results they found was that versus Felipe on ResNet 20, the latency was 2.38 times it was 2.38 times faster, versus Li et al. On AlexNet, the number of rotations, so ciphertext rotations, were 6.41 times fewer. And on ResNet, with comparison with Felipe, the number of bootstraps were also 1.58 times fewer. Also, they did ResNet 50 on ImageNet, which took them 8.98 hours. And also a lot less bootstraps, as you see here, 351 versus 8,480 in He-layers. And yeah, as said, they also did the first high-resolution object detection, which took them 17.5 hours. Yeah, so I'm going to my strengths and weaknesses. So my first strength is that their automated and efficient bootstrap placement is really fast, it's really efficient. And also, as you've seen before, it reduces bootstrap counts dramatically versus prior works on some networks. Then they evaluated on vastly different networks and data sets, 4 data sets, 13 different networks. Also, it is the first paper to demonstrate ImageNet and object detection results. And it's a good thing that they open source their code for reproducibility. Also, it was the latency was improved drastically from versus Felipe on ResNet 20. And also, they reduced the number of rotations a lot. Then the weaknesses. They had some evaluation issues. I mean, they didn't test everything. They ran everything on a single CPU core, which, I mean, they could have tested it on multi-threaded CPU or even GPU, which would have been great to compare because other papers did that and they didn't. So it would be nice to compare the multi-threaded performance. And also some of the HE parameters, for example, the multiplicative budget, they fixed that. And they didn't, they basically constrained the compute graph and didn't explore different HE parameters, especially in their automatic bootstrap placement. If you remember the graph, you can set the maximum amount of levels, and they didn't. They didn't do that for arbitrary HE parameters or different ones. So let's now go to the discussion. First discussion point is, how would you process bigger images? Without, you saw the DRAM was very big. What would happen if we wouldn't be able to fit the images into the DRAM? Do you have any ideas? Yeah.
I have a question. Maybe you could also answer this.
Yeah, I have a question. Maybe you could answer this. So you said earlier that there are 500 gigabytes of DRAM.
Mm-hmm.
Do you know what approximately the encrypted data size was?
The encrypted data size?
Yeah.
No, actually no.
So I'm assuming that.
But do you mean at the size of the images?
Yeah.
I think 32 by 32.
Okay, so but once encrypted, everything fits into DRAM, correct?
Yeah.
So they use such a big DRAM because the data size is so large.
Yeah.
Okay.
But for bigger images, it wouldn't fit into even this DRAM.
So I guess one weakness I would say of the paper is that they only quantify this DRAM, the fact that they use DRAM instead of SSD, so then addressing this kind of discussion point is that basically you'd have a large memory bottleneck where you'd have to consider the time transferring from SSD into the DRAM.
Exactly, yeah.
I actually have a question. Is it the image that takes up most of the DRAM, or is it something else?
No, I think it is the image, the encrypted image.
Are you sure? Like,
Yeah, I think so.
but I think the image takes up one ciphertext, and most of the 300, 400 gigabytes come from the encrypted weights, right?
Oh, yeah, right. Yeah. I mean, you don't have to encrypt the weights though.
Oh, sorry, like the plain
Weights.
text,
Yeah.
encoded weights.
Yeah.
I think I just want to add there that the large amount of data is actually not just from image, but when you encrypt them, you need to have a lot of auxiliary data that needs to be used because it's very complicated. And inside doing some of the operations, you have like large data requirement. They will be like very large matrices, not only image matrices, but large or like intermediate matrices.
Yeah.
And that's why it takes like a lot of data. Yeah.
Okay. So yeah, I mean, you answered correctly. I think the bottleneck would be data movement from storage. Yeah. And also like, how would we improve that? Like, what do you think? Like, how could we improve this data movement and bottleneck?
Yeah, so I think as other works already do, basically you move the computation closer to storage. So you integrate it, for example, with a near storage accelerator or some other thing. Like some people even consider doing in-flash processing for some of these tasks, although this is a less explored domain.
Yeah, I also thought maybe like you could do near storage computation, or maybe like hide the latency because the computation is also really expensive. You could like prefetch something while it's being computed. Yeah, exactly. The second discussion point. Yeah, I mean this bootstrap placement, that's like the novelty or like the biggest point in this paper. Maybe you could also like benefit other applications. What do you think?
Well, there is an alternative approach to string matching, which does not require bootstrapping, which actually Safari has authored a paper on.
Yeah. Yeah. I mean, I think you would have, if you wanted to apply this to other applications, you would need to like do a lot of extra work. Like maybe for some applications, you would need like a different compute graph, maybe not even a DHE. So yeah, I don't think it's like a one-to-one application to other things. Yeah.
I actually have one question before you finish, I guess. Just out of curiosity, you said they basically have a PyTorch API. Do you know what underlying library they use for the actual encryption, these sorts of things?
CKKS. I mean, this.
But which library? So like you can have the CKKS scheme being implemented by different libraries like Microsoft Seal or others. Do you know?
I don't know.
Okay, yeah, that's fine as well.
Yeah, I think I can answer that. It's actually based on Latigo, and it's the backend is done in Latigo, and they provide a high-level wrapper in Python, which is very easy to integrate with the PyTorch framework, as we have seen in the contribution 3. Yeah.
Good. Okay. So yeah, that concludes my presentation. think, yeah.
Yep. I think this is one of the important why this work is very important is because they provide the open source artifacts where it is very helpful, like as someone, if you want to develop something privacy preserving applications. Currently, there's a framework only supports for machine learning, but as discussed in the discussion number 2, I think it will be very good to extend for some general applications and how can you optimize them. Plus, there are many more opportunities like in along these directions, not only for homomorphic encryption, but for other privacy enhancing technologies. And how can you make like bridge the gap between the algorithmic optimizations which are proposed and system level implementation, and how can you make like overall better system implementations. So yeah, this is a good direction to focus on.
Okay, so everyone, thank you for joining. I think this presentation now concludes our series of presenting papers. So a small announcement is that we're soon going to release the final synthesis report. Have already prepared it and it should be online later today. And as always, don't forget to fill the quiz and give feedback now that the semester is over to all other speakers and for your mentors. Okay, thank you very much.